Welcome to Blender for Computational Design. This is the fifth video on the first chapter for parametric geometry. Today we're going to actually be doing a project based on strange attractors. And strange attractors are this really cool looking geometry that comes from mathematical equations. These equations, I think they come from different kind of ways that we're trying to make models to understand things, right? For example, there's the butterfly effect attractor, which is the Lorenz attractor, this one that you can see here, and it comes from trying to understand how the weather works and trying to put these in some equations. And the way they work is that they are chaotic. So that means that if you change the parameters, you're gonna start getting very different results. But they seem to follow a certain pattern. They seem to follow a certain orbits, and follow those orbits, and they never go through the same spot again. Um, if you are interested about the science behind these strange attractors, I'm gonna leave a link for this video from Veritasium, which I think does a really good job explaining the science behind them and how they work. And today's goal is actually gonna be able to create something like this. We're gonna make read the equation for the we're gonna read the equation from Wikipedia or get the equation from somewhere online, and then we're gonna be able to plot these XYZ values. So the way it works is we have a particle that it's moving around a certain orbit. It is a chaotic orbit, meaning that it's unpredictable. We don't know really where it's gonna go, but we're gonna be plotting this in 3D on Blender with Python, right? So hopefully in the end we're able to understand these formulas and how to put them in Python, and we're going to be actually using a function for the first time, how to declare a function, and we're going to look a little bit into doing a material and setting up some basic lighting. um, and actually this project is very inspired in Chaotic Atmospheres collection of Strange Attractors. This has been out for some years now, and he sells these prints of the Strange Attractors that he rendered on Cinema 4D. So as you can see, if you look at for example, this is the Lorenz attractor, the butterfly effect attractor. It comes from these formulas. So we got X, Y, and Z. So this is how we calculate the position of X, Y, and Z on every time frame, on every step that we're going to be taking. So T is going to be time, which is the T here. We're going to have some parameters. In this case, we have sigma, rho, and beta. And well, you can start changing these parameters and getting different results, right? So hopefully at the end you're able to go through these formulas of these different attractors. Some of them are really cool looking, and like this one kind of looks like some kind of furniture or something, but hopefully at the end you're able to read these and be able to make your own implementation in Python inside Blender. So let's get started. Okay, so first, what we're gonna do is we're gonna clean up, we're gonna reuse the file that we did in the last video. Here's where we left off. And the first thing I'm gonna do is I'm gonna actually delete these step inputs, the X, Y, and Z inputs. I'm gonna leave the number input, the vertex output, and the edges output. And I'm gonna delete this code here that right now it's actually calculating the X, Y, and Z position of each one of these points, because now we're going to be using the attractors algorithm to be able to put these points right in the depending on which attractor we're going to do. And well, I'm going to leave this part of the code which appends the point that we're going to create to the vertex list, and I'm going to leave this code which is going to create the edges based on our vertex list. So first I'm gonna refresh this, and right now we are only gonna have one integer input, which I'm gonna plug in here. And in order to get started, I'm gonna start by looking at the formula we want to use. So we have dx divided on dt equals sigma times y minus x. So each one of these equations is for the x, y, and z change every time step. So the time step is gonna be similar to our resolution, right? How close one particle is gonna be to the next. So in this case, what we want to do is start with a really low value, so we have a better resolution. In a perfect world, we could actually have an infinite number of points to represent a curve. That's what the actual equation is representing. But we're gonna have to set time steps into it in order to be able to visualize it. So we're gonna start by creating an x, y, and z values, and we actually are gonna need these parameters, the sigma, rho, and beta parameters. So let's do that for now. So import math, then I'm going to start by x equals 0, y equals 0, and z equals 0. We're going to change these values in a minute, and I'm going to explain you why they cannot be 0, but for now let's leave them like 0. And then we have, we're going to use a equals 10, which is going to be our sigma. Then b equals, if we remember correctly, b equals 8 divided by 3. So b equals 8 divided by 3, which is going to be our beta. And c is going to be, I think it was 28, which is going to be our rho value. So now that we created that, the first thing we're going to do is we're going to calculate if we started actually on the origin 0, 0, 0 in origin of the world. Our next point would be applying the formula and create a small change. So in order to calculate that change every time we're going to iterate here, we need to put that formula. So I'm actually going to use the formula in Wikipedia. So the first formula we have is sigma times y minus x. So let's write down that formula first. So we have our change in x, the x, equals, we said sigma a times y minus x, I believe. Just double check. Yeah, y minus x, right. But now we need to take this dt, which is going to be time. So we need to multiply it by that time step we're going to use. So in this case, we're going to create a new variable, dt equals 0.1 or 0.01 actually. We want a really small value here to be able to see in this space what the equation is doing. So all these, don't forget to put the here. In Python, you actually need to put the multiplication symbol, and then all these, we're going to multiply it by dt. So we calculated the change in x. Now, in order to calculate the next position, so the first position was in 0, 0, 0. The second position is going to apply this formula and it's going to be changed, but we need to add it to x. So x equals x plus dx. That way, every time, every iteration is going to take into account our previous change, and based on the new values, is going to redo this calculation and calculate it again, put it out, and do this over and over, however many times we want to do it. Now, I think we got x. Let's do y. So dy equals, let's check our formula, x times p minus c minus y. So I'm gonna do x times p minus c, so, and then everything minus y. And again, I'm gonna take this whole value and I'm gonna multiply it by our time step dt. And finally, no, well, we need to add it. So this is the change in y. So now in order to calculate the next position in y, it's y equals y plus dy. There's, I think there's, you can actually do these both operations in one line, but I'm doing it this way because I think it's a little more easier to understand what's going on. Now, dc equals, let's check it out, xy minus beta z. So, oh, wait, here we have b, but it's not actually b, it's actually c here. We're, sorry, correcting this one. This one was actually a row, and I used beta there. So dc is gonna be x times y minus beta times c, I think. Yeah, let me see this. Yep, and we're gonna multiply all these by dt. And finally, we're gonna calculate our new z, which is gonna be c equals c plus the change in z. And here we're saving it in a point and appending it to a vertex. Now, there's a problem right now. If I run this, I can actually show it to you. Actually, if you see, we're getting a point there, and if I keep adding points, I think we're getting multiple vertices, origins 332, but we're only seeing one. And the problem is that right now, we're starting on everything zero. So if you remember, we multiply some values. So when we actually are multiplying, when we're multiplying something like x, no, where is it? X times, like here, we are actually, it's zero, right? When you multiply this times this is zero minus y times dt. So we're kind of getting no change at all. So we need to put a little bit of offset from zero so that we can see the change. So there we are, and we're starting to get our strange attractor. And if you see, as I go higher, I get more and more and more, right? Now, the problem right now is this is getting maxed out at 1024. So I'm going to change this max to 10,000. I'm going to see what happens. There we are. So we got our strange attractor. Now, couple things we can actually change. I'm going to actually save this whole code in a function. That way we can look into what functions are. So in order to make a functions, we're gonna start by typing def define, and then Lorenz, which is this type of strange attractor, define Lorenz, and then the parameters. Right now, for example, one parameter we're using is this a number. So we can say this one is n, right? It's gonna take one parameter for now, and then I'm gonna take all this code, and I'm gonna indent it with tab. And then if I run it again, I'm actually not gonna get anything and not change because right now nothing is running. I can see these because it got created before, but I'm gonna delete it for now. So But as you can see, oh, it's actually making it again. What's going on here? All right, is it updating? No, it's not updating. Yeah, so there's an error going on. For some reason, it redraw it, but really right now we're not calling the function, so we need to actually call this function, right? So in order to call the function, we go Lorenz, and the parameter is going to be number, which is going to be the times we're iterating. So these should actually work now. We're getting the origin, so that's working. Okay. This is going really slow, I guess. All right. I'm seeing no changes. So let's see, there's an error going on. Lorenz number. Lorenz. Oh, we're missing an N. So define Lorenz. There we are. Okay, so I'm gonna delete this. And let's see, we get this drawn. So it is getting redrawn. What I'm gonna do for now is I'm gonna delete this and this. I'm gonna redelete this and redelete this. Because what I wanna see is this, the viewer draw for now. So define Lorenz and n is number and range. Okay, and so there we are. So the problem I was having is that right now the parameter that I was putting in did not match the new variable that I set for it. So now number, I use it to call it from here, and then, but this one can be any number, and this is now an internal variable for this function. I don't know if I said it right, but that's how I understand it. Now let's see what's going on. Lorenz. So let's check the system console. Invalid syntax. Okay, so there's a big problem right now, and it's that I did wrong the syntax here. In Python, when you make a function, you actually need to close it. This, when you define it, you close it with a column. So there it is, and nothing. No. Okay, so we're getting our list of points, as you can see now. I'm gonna refresh these. Oh, here it is, turn off. So 260, it's growing, and there we go. All right, so it's working now. Oh, something that you can do to debug too sometimes is, remember, you can actually bring in a text editor, and it can be any of them really, and plug in the data and see what type of data we're getting here, what type of list, and how the numbers are coming out. So right now it looks like it's working. What we're gonna do before we start working on the material and making a render out of this is we're going to actually add another parameter. So right now the only parameter is driving how many times we're iterating here, but now I actually want to be able to change from my nodes the dt. So let's create that, n, and then dt as the equals, our default value is going to be 0.01, and the nestedness level is going to be also 2. So we create our input. So now we actually don't need this here. So here, comma, dt, or we can call it t here, and then actually multiply everything here by t. And so I'm fitting the dt value I'm gonna get from my node to the t value in my function, and then it's gonna call it right here. So let's see if this works. We created a new value here, dt. So we actually can get this, shift D. I'm gonna change this to a float, 1001. 0.001, for example. I can plug it in, and then can, as you can see, we can change in real time these values. I'll try it from here maybe. Okay, so there you go. So 0.01, 0.04. As you can tell, the distance between each one, it decreases the smaller the number is. 0.005, we should get more points. But then we run out of points before, so we need to add more more points here, right? But we can actually keep going probably lower here or higher depending on what we're looking for. I think this looks pretty good. Um, Actually, maybe even less than that for what we're gonna do. So now we have this parameter coming from here. Now, we can add another one. So the one I'm gonna actually add right now, it's gonna be sigma. We're gonna change sigma. So in sigma as default is gonna be 10. Nestedness equals 2. So we create our input for the sigma value, and now we're going to call it here. No, actually we can leave it for now like that because sigma is here, and what I can do here is just change it here. Sigma. Well, I can actually put it here. S. And then here, sigma. So again, what I'm doing is I'm gonna feed a new node value here that is gonna get in the input sigma, and then I'm gonna use when I call the function, the Lorenz function, I'm gonna feed the parameter sigma, which then is gonna write actually your sigma from that. But here I have an error because I'm actually calling the sigma from out here, but I should call it from our parameter here. Now, again, I can now change this, and as you can see, we can change in real time our strange attractor. Now, in the final part, we're gonna just focus on making a material, making a thick geometry here using some modifiers. But I really want to encourage you guys for now to go to chaotic atmospheres. And before you keep going with the tutorial, I will love it if you actually pick another one here and actually try to grab the equation for whichever one you like and put it in your put in your script and then keep going. So that's gonna be the task for now, and we'll be back trying to make it look really cool. Okay, guys. So I did all the lighting and everything, so I'm gonna explain it because it extended the whole tutorial for another 20 minutes. So if you guys are interested, I'll post that video that I that I recorded. Uh, but it was too long to spend on just the visualization part. So I'm gonna go real fast and explain what I did. So I extruded this plane that I had here. I beveled these corners. I added the sun, right? And I make sure it was illuminating these both faces of my background now. I added a camera, so spend some time actually trying to find a good camera angle. I think that's gonna be very important on the final product that you're gonna be rendering. I also added a couple lights because of the size of this. This is huge. Like if I had a cube, like a with if I had a cube here, Shift A, see how small it is. So my scene is huge. This strange attractor became humongous. Of course, we can scale it down, but I added these lights. I added some color. I had to bump it up to 3,000 watts, which is a lot. And what I did was two things. So the first way to achieve this was to achieve actually this look, the medable look. Um, I'll show you how it looks without all this stuff. Oh, there it is. I'm gonna turn this off too. So this was one of the views, and I'll show you the final render product in a minute. I'll put it at the end of the video. But in order to achieve this, what I did is really simple. I click Shift A, this, and then pick the meta ball, plug it in there. I'm gonna hide this. And actually, let me turn some things here. This up. And what I did is I plugged in my vertices to my origins here in the meta balls, and it gave me that cool looking kind of material. Now, there's two things you can do. One is like we can have that metallic material, only bump this up, get a nice color that you like. Again, oh, wrong material. We're talking about this one. So you can bump up the metallic here, right? Make it look like aluminum or whatever metal that you like. Um, but the very important part, I think, is adding those lights. Those lights that I showed you a minute ago made a huge difference on all the reflections on the dark side here, right? This was really really. So if I turn off actually those lights, maybe you can see it. See the like those lights I'm turning off in the people make a huge difference. So like get a nice angle, get some lights. And as you can tell, I have two lights. One is kind of warm and one is really cold. So this is one of the ways that you can make a really cool render from this. Now, if you're gonna go with the look for chaotic atmospheres, if you see he's like taking this kind of star shape here and extruding it around it. So the way I did that, turn it off. Um, Turn it off here. Oh, it's this one. Sorry. So the way I did that is actually it's this one. So the way I did that is same thing. I actually baked this, my viewer draw. I baked it. So that gave me this new object, right? If I bake it, it's gonna create a new object for me. And what I did is I selected this object. Let me shut this on one. And I converted it, so converted it to curve. And once it's a curve, what I do is I go to this curve in the pan in this panel here, go to curve, geometry, bevel. I take the object and I picked a polygon that I did. And this polygon that you see here is this one here. So this is a curve. So the way I did it is I activated the extra objects add-on, the curve add-on. So if I actually go in and show you, let's see, extras. All right, there we go. So it started with an hexagon, I think. Then I subdivided that curve hexagon, and then I I took the two innermost um, control points, right? So well, right now it's super slow because it's actually um, these changes are reflecting in real time on my object. But yeah, I made it an hexagon, subdivided, and then inserted these two control points. So just make a curve that looks like a shape that you want to extrude it in. You can actually close the caps, fill caps. Okay, wrong one. It's this one. Fill caps. So that looks cool. 0, and there you go. The same render again. Go to the materials. We can pick this metallic material that we were looking at in a second ago. And actually, another material that you can try is just take up the subsurface, right? And let's make it a little bit yellowish. So you can make it look like this kind of bone kind of ceramic look that you can give it. Now, as you can see, sometimes you get these lines, right? So to get rid of that, go to Object and click on Shade Smooth. If it's still a little bumpy, like here, you can actually see how it's bumpy. You can actually go and have a subdivision surface, and that should repair it. All right, guys, I hope you liked it, and please share whatever you create with this. And in the next videos, we're gonna actually start making some surfaces and other things. So faces and surfaces, and start adding another list of objects, or another list of we have a vertex list, we have a edge list. Now we're gonna have also faces and define our faces and surfaces. So see you in the next videos.